Okay, so linear equations, right? You probably think you've got them down. I mean, x plus 2 equals 5, that's like, what, second grade? But have you ever, like, actually thought about what's going on in your head
Mm-hmm.
when you solve these things? Like, why do some equations just, like, feel so much harder than others?
Yeah, it's really fascinating, isn't it? It's like you think math is all about like a straight line of difficulty, but when you actually look closely, it's way more nuanced than that. There are all these like hidden layers.
Totally. And that's exactly what we're diving into today. Welcome to the deep dive where we deep dive. And today we're tackling linear equations. And like, not just how to solve them, because, we're assuming you could do that already.
Yeah, we're going way deeper.
Exactly. We're using this really interesting research article called Unpacking the Complexity of Linear Equations from a Cognitive Load Theory Perspective by Bing-Hong Gu and Wee P. Fan.
And basically what we want to understand is why some linear equations are like a walk in the park, while others feel like climbing Mount Everest, mentally speaking.
Right. And the key to understanding this is something called cognitive load. It's like the amount of brain power you need to use to process information. So we're going to figure out what makes some equations just like demand more from our working memory.
And it turns out the whole like one step, two step, multi step progression, it's not just about adding more steps. There's a really like elegant underlying structure to it.
Okay, so the article starts off by talking about how incredibly important linear equations are in like math education all around the world. Like TUMTEST, the Third International Mathematics and Science Study, they found that teaching equation solving is like a core part of the lower secondary curriculum pretty much everywhere.
Yeah, it's like a universal building block. Math teachers everywhere, they know it's a fundamental skill.
Makes sense, right? Because as the authors point out, linear equations are basically the bridge between like pre-algebra, where things are more concrete, and the more abstract world of, well, algebra.
And we know from research, like by Humberstone and Reeve and Kieran, that algebra is super powerful for problem solving. It just like opens up a whole new level of thinking.
But, and this is the big but, that transition from arithmetic to algebra, it's not always easy. The National Research Council, they actually highlight it as a big challenge in math education.
Yeah, and a study in Australia by Stacey and McGregor found that only about 30% of middle school students could even set up an equation from a word problem, which, like, that's the first step. If you can't do that, you can't even start solving.
Exactly, you're totally stuck. And the authors, they really emphasize how important it is to have a solid understanding of solving linear equations. Because if you don't, it's going to make it way harder to tackle more complicated problems later on.
So, like, not just for algebra, but for anything that builds on those skills.
So, we've always sort of had ways of classifying linear equations, like we call them first-degree equations, or
Sure.
there was Vlasis who talked about, like, concrete versus abstract equations.
Right, like x plus 7 equals 5 would be more concrete, and then something like 12 minus x equals 7 would be more abstract.
And then there's Peakrey and Martin, who laid out, like, a sequence from x plus b equals d all the way to x plus b equals cx plus d to show increasing complexity.
But the problem is, these ways of classifying, they haven't been very systematic, and they don't really help us understand, like, the nitty-gritty of why some equations are harder than others, especially when you throw in things like negative unknowns.
Yeah, that makes sense. So these researchers, they're proposing something totally different, right?
They are. They're using this idea of operational lines and relational lines, which comes from cognitive load theory, to explain complexity. And it's like a whole new way of looking at things.
Okay, so can you break that down for us? Like, what exactly are operational and relational lines? I mean, I'm not a cognitive load expert or anything.
Yeah. Sure. So an operational line is basically any action you take to change the equation while keeping it balanced. Like adding or subtracting something from both sides, or multiplying or dividing both sides by the same thing.
Right, the stuff you do to actually solve for X.
Exactly. And a relational line is like a snapshot of the equation at a particular moment. It shows the relationship between all the different parts of the equation, like the unknown, the numbers, the operations.
So it's like the state of the equation at that point in time.
Exactly. And to illustrate this, the authors use a really simple one-step equation as an example. It's x plus 2 equals 11.
Okay, classic one-step equation. Let's see how this works.
So the first line, x plus 2 equals 11, that's a relational line. You've got three elements there, x, 2, and 11. And implicitly, you're dealing with the concepts of the unknown, equality, and balance.
Okay, so that's like the starting point. What's the next line?
The next line is where you subtract 2 from both sides, right? So minus 2, that's an operational line. Here, the main element is the -2, and the key concepts are canceling out the +2 and maintaining balance.
And that gets you to the solution.
Yep. The third line is x equals 9, which is another relational line. Now, the relationship is super simple, just x and 9, and they're equal. And the authors point out this thing called element interactivity, which basically means your brain has to process both the relationships between the elements and the operations you're performing at the same time.
So it's like a lot of juggling going on in your head.
Exactly. So the idea is that as equations get more complex, the number of operational and relational lines increases, which means more element interactivity and therefore more cognitive load.
Okay, so like a two-step equation would have more lines than a one-step equation.
Exactly. Let's take, for example, 2x plus 3 equals 7. The first line, 2x plus 3 equals 7, is relational. Now we have four elements, 2x, 3, 7, and the multiplication. And more concepts in play, like order of operations.
Right, so more to keep track of from the start. What's the next step?
Well, you'd subtract 3 from both sides, which is an operational line. That gives you 2x equals 4, another relational line. Then you'd divide both sides by 2, another operational line. And you end up with x equals 2, a final relational line.
So two operational lines and three relational lines in total, more than the one-step equation.
And the authors point out something really interesting here. They say that once you've done that first operational step in a two-step equation, what you're left with is essentially a one-step equation. Like in our example, 2x equals 4.
So it's like a one-step equation nested inside a two-step equation.
Exactly. They call it a derivative of a one-step equation.
Okay, that's pretty cool. What about multi-step equations, like the ones that just look really scary?
So let's take an example like 3x minus 2 equals x plus 4. The first line, that's relational, and we have four elements, 3x, 2x, and 4. Plus all those concepts like multiplication, subtraction, addition, equality, and balancing.
Yeah, it definitely feels like there's more going on there.
Right. Then a common first step would be to subtract x from both sides, which is operational. That gives you 2x minus 2 equals 4, which is relational. Then you'd add 2 to both sides, another operational line, resulting in 2x equals 6, relational again. And finally, divide both sides by 2, operational, to get x equals 3, our final relational line.
So three operational lines and four relational lines, even more than the two-step equation.
Right. And if you look at it, after that first step of subtracting x, what you have is basically a two-step equation. So again, it's like a two-step equation nested inside a multi-step equation.
Okay, so there's this clear hierarchy. Multi-step builds on two-step, which builds on one-step. And the more lines you have, the higher the cognitive load.
But it goes even deeper than that. The authors point out that even within each category, like one-step, two-step, multi-step, there can be big differences in complexity.
So it's not just about the number of steps.
Nope. It also depends on the specific number of operational and relational lines you need for that particular equation and the types of numbers and variables you're dealing with. They call these simple and complex elements.
So like fractions and decimals would be complex elements.
Exactly. And negative numbers, negative unknowns, percentages, anything that requires a bit more mental gymnastics.
Makes sense. So like an equation with a fraction is going to be harder than one without, even if they both have the same number of steps.
Right. And the article gives a bunch of examples of this. Like for one-step equations, they compare x plus 5 equals 12, which is pretty straightforward, to something like a minus 3 equals minus 7, where you have negative numbers, or 10 minus n equals 0, which has a negative unknown.
And they even did a study that showed students actually had a harder time with those equations with negative numbers and negative unknowns.
Exactly. And they do the same thing with two-step and multi-step equations, showing how different types of elements can make them more or less complex.
So what does all this mean for like actually teaching and learning algebra?
Well, the big takeaway is that we need to be really careful about how we sequence instruction. We should start with equations that have fewer lines and simpler elements and gradually introduce more complex ones.
So like building up slowly, making sure students have a solid foundation before moving on.
Exactly. And the research also shows that work examples are super helpful for building those mental schemas. Like, seeing how a two-step equation is solved can help students understand how to solve a multi-step equation.
And this framework, with the operational and relational lines, gives teachers a much more nuanced way to think about how they classify equations in their lessons and textbooks.
They even suggest using a new notation, like n-step and n+1-step equations, to really reflect the increase in complexity.
Well, that's interesting. So instead of saying two-step equation, you'd say three-step equation if it has one more operational line.
Precisely. And the article also talks about different methods for solving equations, like the flexible method versus the distributive method, and how this framework can help us understand why some methods are better suited for certain types of equations.
And they really stress the importance of explicitly teaching those complex elements, like making sure students are comfortable working with fractions, decimals, and percentages in simpler equations before throwing them into more complicated situations.
Because if they don't have that foundation, it's going to be really tough for them when they encounter those elements in higher level math.
So the main point here is that the complexity of linear equations is about way more than just the number of steps. It's about the interplay between the operational and relational lines and the types of elements involved.
And understanding this, it not only gives you a deeper appreciation for algebra, but it also tells you something about how learning works in general. Even seemingly simple things can have a lot of hidden complexity.
Right, so the next time you see an equation like, I don't know, x minus 1 equals 4, you can think about all the mental steps involved, especially if you're still learning about negative numbers.
And here's a question for you to think about. How does this idea of operational and relational lines apply to other things you're learning? Like, what are the actions you take and the relationships you have to understand in those areas?
Yeah, that's a good one to ponder. And if you want to learn more about all this, definitely check out the original article. It's called Unpacking the Complexity of Linear Equations from a Cognitive Load Theory Perspective by Bing-Hyung Gu and Wei Pifan. It's a really fascinating read.
It really makes you think differently about something you probably thought you already knew.
Thanks for joining us for this deep dive.
It was my pleasure. Always fun to explore these hidden depths.